Hello and welcome to codeinpractice.com. In this tutorial we'll be talking about binary arithmetic. Now if you want to get a deeper understanding of the data types and why their ranges are what they are, binary arithmetic is an essential, and it is also good to know binary arithmetic if you want to be a better programmer. So before we begin, let me show you something. There are only 10 kinds of people in this world: those who know binary and those who do not. Now, if you're wondering what happened to the other 8 kind of people, you are in the right place. So, to begin with, we know that a computer stores the data in the form of zeros and ones, and that's all fine, but except that we don't understand ones and zeros. We need to know how a computer thinks in zeros and ones, and we need to know binary. So first things first, the smallest indivisible unit of data is a bit, right? So if you imagine a bit to be like a box that can store only 2 possible values, a 0 or a 1, so it would look something like this. Here's a bit storing value 0 and here's a bit storing the value 1. Now this system is called the binary because it can only store 2 values, 0 or 1. Now imagine 8 such boxes stacked together. So we have 1, 2, 3, 4, 5, 6, 7, 8 boxes, and each of them has a value. It can be either a 0 or a 1, and this collection of 8 bits is known as a byte. So now that you know what a bit and a byte is, we still have one question left. How do we convert the normal human readable data to binary that a computer will understand? Now to answer this, you need to think back to your elementary school days and how we learned to count. So if we had a number called like 438 and we needed to represent that number, how we did that was we had the hundreds, the tenths and the ones place, and we took the first number, we stuck it at the hundreds place, took the second number, stuck it at the tens place, and we took the last number and stuck it at the ones place. And what these places is that they were the powers of 10. So 10 raised to the power of 0 is 1, because anything raised to the power of 0 is 1, and then 10 raised to the power of 1 is 10, 10 raised to the power of 2 is 100. And as you can see, there were powers of 10 because it was a decimal system, which meant that it had 10 digits. So 4 into 100 plus 3 into 10 plus 8 into 1 is 400 plus 30 plus 8, so 438. Here's another thing that you may like to imagine, and it will make things a lot easier. Think of a car odometer, odometer that tells how many miles you have driven. So if you have a car odometer that is set like this, 000999, that means you have driven 999 kilometers or miles, whatever, and the positions are about to be reset because you are going to drive 1 more mile. So if you drive 1 more mile, this this dial will rotate by 1 degree, right? So it will go up and it will be set to 0, which will cause this dial to be set to 0, and that will cause this dial to be set to 0, and that will cause this dial to increment by 1. So this will be at 1 and the others will be at 0, and as you can imagine how it keeps on rotating and bringing up next values. So with those things in mind, let's imagine a binary odometer, right? And by binary I mean that we don't have the other 8 values, we only have a 0 and a 1, right? So if we began our journey from 0 kilometers, so our odometer would look something like this. It's all set to 0 and the value 0. These boxes represent what the value is in decimal, right? And this is the binary counterpart, or this is the binary odometer, if you will. So if you drive 1 mile, this one sets to 1 because after 0 there is 1, right? And then what happens is we drive another mile, and now after a 1 there is only a 0, there is no 2. So this resets to 0 and it causes the next dial to be incremented by 1. So that's why a 2 in binary is represented as 1 0, and now you know it's not a 10, it's a 1 and a 0, and now you know what happened to the other 8 people. So what about 3? So this 0 again sets to 1, and that's a 3. So 1 1 means 3 in binary. What about 4? Both are 1, so this goes up by 0, and this causes this to go up by 1, and it sets to 0, and this causes this to flip and be set to 1. And for 5, this sets to 1 because it is incremented by 1, and then so is 6 because this is incremented by 1, and it causes this one to be incremented by 1. So this gets set to 1 and this gets set to 0, and so on for 7, and then 8, and then 9, 10, 11, 12, up to 15. One more thing that we need to observe is, in decimal we had 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then what would happen is that a 0 would be placed over here, and then a 1 would be placed over here, and the 1 would remain constant throughout, and these values will keep incrementing just like they were incrementing over here. So if we have a 10, we have a 0 at the end. If we have 11, we have 1 at the end. If we have 12, we have 2 at the end, just like this. And if you look at the binary numbers, something similar happens over here as well. So if you see the last two columns, the last two bits of each binary number on the left hand column and on the right hand column, you will see that the last two values are exactly the same, only the front bit is changing. So as you can see that we have 0 0 0 1 1 0 1 1, and then we again have 0 0 0 1 1 0 1 1, and that this pattern continues on. So now that we know how to count in binary, how do we convert? Now we are not going to count a binary for some number like 0 1 0 1 0 1 0 0, right? So how do we convert? Here's how we convert. Just as we had the ones, the twos, and the thirds place, the ones and the tenths and the hundredth place in normal decimal system, we have the power of twos. So we have the 2 to the 0th power, we have 2 to the first power, 2 to the second power, 2 to the third power, and so on. And what you need to do to convert is just write the number over here above, and below that just write the power associated to that particular position. So we begin from 0 because we are programmers, we always count from 0, and we have 2 to the power of 0, which is, well, just 1, and then we have 2 to the power of 1, which is 2, and these are the values that are over here. You may want to use a calculator to calculate these values, and that's fine. So what we need to do is multiply this value by this value, and now we are only going to multiply the values where the value of the binary digit is 1, because 0 will cause it to be 0. So 2 raised to the power of 2 multiplied by 1 is 4. 2 raised to the power of 4 is 16 multiplied by 1, again 16. 2 raised to the power of 6 is 64 multiplied by 1, 64. And then we add all these numbers up and we get the result as 84. That's all fine, but what about the other way around, right? So that's also easy. Just keep dividing the numbers by 2 and keep on storing the remainders. So if you have the number 84, we divide that by 2 and we get 42, and the remainder is 0. 42 divided by 2, remainder again 0. Then we have 21 divided by 2 and the remainder is 1. 10 divided by 2, remainder is 0. 5 divided by 2, remainder is 1, and then 2 divided by 2, the remainder is 0. Now we are left with the 1, right? If you're left with the 1, what do? You divide 1 by 2, and we can only divide by whole numbers. We cannot divide by fractional parts. So 2 multiplied by 1 is 2, which is greater than 1. We need a value that is lesser than 1. So what do? We just multiply the 2 by 0 and we get the value 0, and 1 minus 0 is 1. Or if this seems a little bit too complicated, if you get a 1 over here, just stick this over here. Just take this 1 from here and just put it over here. And now to get the value, what the value is in binary, all we need to do is just write down the numbers from bottom to top. So 1 0 1 0 1 0 0. So that's the number we have, 1 0 1 0 1 0 0. And if you want to make, this is only 7 bits, and if you want to make it look like a byte, you can just stick a 0 over here and that will look like a byte, because now it has 8 bits. It has 0 1 0 1 0 1 0 0. So that's all fine, but we have another question. Why is the range of a data type what it is? And also, what about characters? They are not stored as numbers, or are they? Characters range from 0 to 65536, and that's because they use 16 bits or 2 bytes of space. So we have 8 bits over here and 8 bits over here, and that's 1 byte and a 2 byte. It turns out that characters are stored as number in Java, but Java knows that it's a character. So when so it converts the value to a character when the program is run. Now you can verify that this is the range, or these are the total values that this character can store, because if you have 16 bits, right, and if you set each bit to 1, so 1 over here and 1 till the very end, that will mean that this entire value is absolutely full. And if you were to convert that using the previous method, you would get that the maximum value that could be stored is 65536. So each character has a number associated with it. So if you are storing some value in a character, so if you for example store the value p in a character variable, that p is looked up on a table which has all the different kinds of values for each character. It takes the value from that table, converts that value into binary, and feeds it into the character data type. You can download the ASCII chart, which shows the mapping of what numbers map to what characters. Now that we have discussed character, what about numeric data types? We have byte, short, int, and long, and all of them are signed. What signed means is that there is a part in the value that represents the sign of the number. By sign we mean whether it's a positive number or whether it's a negative number. So if we imagine a byte, we have 8 bits, right? The leading bit is taken out, and the remaining 7 bits are the ones that are used to store the value. So this bit can be either 0 or 1, and a 0 would represent a positive number and a 1 would represent a negative number, and this 7 bits keep track of the numeric values. So we have 7 bits for numeric part, so we have 2 to the power of 7, and that means 128, which means we can store 128 positive values and 128 negative values. So the question is, why is the range of the byte from negative 128 to positive 187 and not positive 128? Well, that's because 0 eats up one value, because after all we also need a binary representation of storing 0, and 0 is stored as a positive number, so that's why we have 1 less on the positive side. So 0 is stored like this, 0 and then 7 zeros followed after it. So this represents a 0, and this then represents the other numbers. So similarly we can use the same logic and find out the ranges for every other numeric data type. So we have short, which is 16 bits, because it is short is of 2 bytes, which means 16 bits, and 1 bit is for the sign, so we are left with 15 bits, and 2 to the power of 15 is 32768, and that becomes negative 32768 to positive 32767, and not 8, because one position is for the 0. Similarly for int, int is made up of 4 bytes, which is 32 bits, and 1 bit is subtracted, and 2 raised to the power 31 is this number, and so we have this range. And similarly for long, we have 64 bits, because long is made up of 64 bits, and 1 bit is less for the sign, and we have 2 raised to the power 63, which is this big a number. And again, if you'll notice that it's from the last number is 808, and on the positive side we have 807. So that's it for the numeric types. What about Boolean? It just stores true and false. All it has to store is whether a value is true or whether it's a false value. Some say it's a byte long, some others say it's a bit long. I really don't know, but if someone asks you, just tell them this, that it's virtual machine dependent. And what that means is that depending on what virtual machine you're running, whether you're running on a Windows machine or whether you're running on a Linux machine, you're using 32 bits or you're using 64 bits, it just depends on the virtual machine type and what it has implemented, whether it has implemented it as a bit or whether it has implemented it as a byte. That leaves us with float and double. What about float and double? Well, float and double are a bit complicated topic, and I won't confuse you too much. I just want you to know this. All you need to know is that floats are made up of 32 bits and doubles are made up of 64 bits, and both of them store fractional values. So obviously, because float has only 32 bits and double has 64 bits, floats can store lesser values, I mean values which are smaller, and doubles can store really large values. So if you try to stick a float inside a double, that's fine, because a double is bigger than a float. But the reverse is not true. You are going to lose bits. So imagine a 64-bit container, right? And then you want to stick that into a 32-bit container. Obviously you have to lose something, right, to make it go in. That's why when you compile, the compiler will say possible loss of precision. So when you try to put a double value into a float value, the compiler will complain. And if you have declared a float variable and you are trying to put in the value 5.0 inside it, that's fine. That's a very small number and there's no problems with that. But the problem is that if you write 5.0, the compiler thinks that it's a double value. To say that it's a float value, you must write the F at the end of it, so that you are telling the compiler that no, it's a float value and I know what I'm doing. So you can stick the value into the variable. So it says possible loss of precision if you don't use the F, because you may lose bits or you may not lose bits, because if you have a number that is within the range of a float, but you have not appended the F, it's still a double. So if you stick it into that, you will retain the value. But if you had some bigger number, right, that was out of the range of a float, you may lose the value, right? So that's why it says possible loss of precision, because it's a possibility and not a surety. So what about the F and L business? Why do we need the F and why do we need the L? So let's talk about L first. If you're going to assign a number greater than this number or less than this number, you must specify the L prefix to let the compiler know and yourself that you are going to use a long value and that the compiler should check if it's a long variable. So if you are going to use a value that is greater than this, you should know that you are using a long value, because anything that is greater than this or less than this is in the range of a long variable, as we discussed earlier. So if you put a L at the end, you know and the compiler knows that it's a long variable and that it should be kept inside a long, right? And now about the F. All fractional values default to doubles. So if you write 5.0, that is a double and it should be stored in a double. But if you want to store it in a float and you know that it's a very small value, for example, if you're going to store values of the salaries of people and they're never going to be that big, so you want to use float to save this storage space. So you want to put a F at the end, a small f or a capital F, to let the compiler know that you are losing precision and you are okay with that. To end this, I just want to give you a piece of advice. You may use the small l or the capital L, but it is best to use the capital L, otherwise it may look like a 1. And now what I mean is that if you have a number like this, 2154187, and you want to tell the compiler that's a long number, don't use the small l, because now it looks like this and it starts to look like this, right? So this looks like a 1 at the end, right? So use this. So now this looks what it should look like. This looks like the number followed with an L at the end. So I hope this tutorial helps you in understanding data types and variables in more detail, and thank you for viewing.